Okay, cool. Thank you, Guillermo. So thanks for the introduction. So and yeah, it's just to make a precision. I was at ANU, but I just left, and I'm going to start another postdoc in Birmingham in early January. But anyway, so yeah, so today I'll be talking about a work that I've done conjointly with Dominik, and that's about providing a succinct and verified completeness proof for first-order bi-intuitionistic logic. So I'll try to give you an idea about what bi-intuitionistic logic is, despite the fact that I think that you had already an introduction earlier today by John T. And then I'll move on to what is our succinct and verified completeness proof and what its structure is roughly. So, okay, so let's start with what bind is. As you may already know, bind in a propositional case is just an extension of intuitionistic logic with this binary operator that's called exclusion, which is in red here, and that is dual to the implication. And so you're meant to read it as phi excludes, well, let's say that there is a psi on the right of it here. And so that's what you extend the language of intuitionistic logic with. So that's from the syntactic side of things. And on the axiomatic side of things, you just take an axiomatization plus the modus ponens rule for axiomatization for int, and you take the modus ponens rule, and then you expand it with the axioms that are listed, as well as the rule that you must have already seen earlier today. And these are axioms are somehow the dualized properties of the implication, and which are describing the behavior of the exclusion. From the Kripke semantic side, this logic is captured by the same semantics as Kripke semantics as intuitionistic logic for the propositional case. So you have your usual Kripke frames, which are pre-ordered sets where the relation is transitive and reflexive. You have persistence of the atoms through the relation of accessibility relation, and you also have you need now to interpret the exclusion arrow because that's something that you added to the language, and the way that you interpret it is in the following way. So you have that phi excludes psi is being made true at W if you've got a predecessor V such that V satisfies phi but not psi. So if you think about the implication, which looks at all of the successes of a certain point W, the exclusion will look at one, so the existential of a predecessor of W. And so that's why you can see some sort of duality. And so it's well known that the axiomatic system and the Kripke semantics so described sort of correspond. So you've got a soundness and completeness result. But now that we know that the semantics is the same one for intuitionistic logic and binds, we've got the same frames, then we know that bi-intuitionistic logic in a propositional case is a conservative extension of intuitionistic logic. So on the fragment without exclusion, they do coincide. That's for the propositional case. So, but we want to talk about first order. So what happens there? In the first order case, then you need to introduce variables. Our variables here will be natural numbers. That's something that will pop up further down the line in my talk. And we need to have function symbols so that we can create terms. And we also need some predicate symbols so that we can create atoms, pt, for example, p vector t here. And then what we do in the syntax is we extend the syntax with quantifiers, the universal and existential ones. So that's from the syntactic side again. Axiomatically speaking, there are two ways you can think about first order bind. The first one is you take the propositional bind and you add all of the axioms and rules that are describing the behavior of the quantifiers that you can see on the screen. Or another way to perceive that is that you just take first order intuitionistic logic and then you add all of the axioms and rules on the slide before describing the bi-intuitionistic part of the logic. So essentially, in a propositional and first order case, you do the same trick of adding just the axioms that are describing the bi-intuitionistic connective to intuitionistic logic. But now the surprise is, while in the propositional case we had a conservative extension, in the first order case this is not happening. We have that first order bi-intuitionistic logic can prove a formula that is expressed purely in the language of intuitionistic logic, and that is not provable in first order intuitionistic logic. This formula is the one that's displayed on the screen, and that's called the constant domain axiom. So if you read it, it sort of allows you to push inside of a disjunction a universal quantifier under the condition that a psi does not have a x3 in it. So, okay, so now that we know that they are not coinciding on the intuitionistic fragment, we know that it can't have the same semantics, first order bind and first order int. So what's the Kripke semantics for first order bind? Well, the formula that distinguishes the two of the logics is called the constant domain axioms. This axiom has its name for a specific reason, which is that it's capturing in the language of intuitionistic logic the Kripke frames which have a constant domain in the first order case. So let's give it a crack and let's see what a semantics like this would look like. And so you just have your usual frames, the preordered sets that we had before, to which you're just adding one constant domain D, which is the domain for all of the points in all of your frame. And then you also make sure, again, that you have persistence of the atoms as well as an assignment function that tells you how to interpret variables, so var to D. And then what you need to do is you need to take the same interpretation of the connective as we had before, but this time you also need to interpret the quantifiers. And the quantifiers are interpreted a bit like classically to an extent, in the sense that at a world W for all x phi, it is holding if all of the elements of the domain are satisfying phi once you substitute x by the element D, essentially. And note that on the contrary to the intuitionistic case, we don't need in the constant domain case to interpret all the universal quantifier on all of the successors. And in the existential case is similarly done. So an existential formula phi is true at a point if there exists an element of the domain that is satisfying phi. And so what we're hoping is that we have a completeness result for first order bind, and then we would get as a consequence that first order bind is a conservative extension of first order constant domain int. And well, the thing is, these completeness proofs have been provided in the past by Klemke in 1971 and Rauser in 1977. So at this point in the talk, you should tell yourself, well, what are these two guys on about if they are trying to give us a presentation about the completeness proof of first order by intuitionistic logic while they already exist in the literature? So what's the point of all their work? The thing is that these proofs are not really proofs, in the sense that it's been already discussed, and notably in my thesis quite at length, that Rauser has a lot of mistakes in our completeness proofs. And the one by Klemke is German, it is in German, not necessarily that makes it incorrect, but it's quite difficult of access. It is also technically rather difficult, and it does allegedly contain errors. And so that's something that's been picked up by Grigory Kovikov and Guillermo Badia. And yet, Dominik, being a German speaker as well, had a read of the proof and could not be convinced either way that it was correct or incorrect. So let's say that there are general doubts about the general proofs of completeness in this realm. So that's exactly what we're doing. What we're doing is we provide a completeness proof that is a correct proof, in the sense that we can claim this correctness because we verified all of our arguments in coq/roc. It's rather succinct, so that's in contrast with the potential proof of Klemke, in the sense that we could write the entire proof and explain everything into only 15 pages, and that's a paper at CSL that we just got accepted in 2025, so next year. It's also rather standard proof because it does a usual canonical model construction and uses quite standard machinery that I will explain further down the line. But still, it's not entirely boring, in the sense that we did provide a novel element that's a dualization of an already existing argument that's out there in the literature that we call the dual constant domain Lindenbaum lemma, and I'll tell you more about this later on. Okay, so what I'll do is I'll tell you first try to remind you roughly how we do a prove our canonical model construction. Then I'll delve into the details of this proof in our specific case of first order binds. So how do we do a prove our canonical model construction? The first ingredient that you need is you need to have a canonical model, rather obviously. And most of the time, this canonical model needs to have a frame that has a set of points which are theories of a certain kind. So you need to have certain properties on these theories. Theories meaning sets of formulae which are closed most of the time under deduction, but also consistent. Plus, you need some properties, like they can be maximally consistent set, they can be prime, blah, blah, blah. So we'll have to determine what we want in our case. Most of the time, you also have an accessibility relation, and in most cases, it is the inclusion. So that's what we see here, the set theoretic exclusion. And we'll have as our constant domain just the terms, because it's a syntactic model and you will interpret terms as themselves in this model. So with this model, we want as a second ingredient that it satisfies a very strong property, which is equating elementhood, so set membership, with forcing. So what we mean by this is that the theories in this model that we have have a dual nature. So at the same time, they are sets of formulae, but also there are points in the model. And what we want to say is that a formula is an element of this theory if and only if this formula is forced by this very theory. And so that's a key component of the proof. And the last element is that we want to be able to project any consecution delta phi, which is not holding, into one of these theories. So that we want to generate from the non-holding of the consecution delta phi a theory gamma such that delta is included in gamma, meaning that all of the formulae in delta will be true in the point in a canonical model corresponding to gamma, but also making sure that phi is not included in gamma itself, meaning that phi will also be false at these very points. So we would then have a witness to the non-holding of the semantic entailment. Okay, so that's what we're going to do. In the abstract, that's how you do them. And what we're going to do is we're going to explain how you do a canonical, what our canonical model looks like, and what our Lindenbaum lemma looks like, and then we'll try to build up the truth lemma on the way. Okay, so canonical model. So what do we want our theories to be like? Generally, the properties of the theories that we'll want to have will be dictated by the truth lemma. First of all, we want our theories to be prime. What that means is that if a theory of if a prime theory has a disjunction in it, then it needs to witness this disjunction by having one of the disjuncts inside of it. Why do we want this property? Well, because if you have a disjunction in a prime theory, that implies that one of the disjuncts is in the theory. And so remember that usually the truth lemma, we prove it by induction on the structure of the formula. So in the truth lemma context, we'd be able to apply the induction hypothesis here, which would equate membership with forcing. So that would entail that if one of the disjuncts is in gamma, then gamma has to force one of the disjuncts. And so that means that gamma forces the disjunction. So we can bridge then we can prove one of the direction of one of the cases of the truth lemma by making sure that our theories are prime. And so we'll do the same for the quantifiers. And so we'll require that our theories are Henkin. So we'll go for each of the quantifier, we'll require a specific property. The first one is for the existential. So we want to say that if a theory has an existential in it, then it needs to witness it. We're using a specific variable k showing that the existential formula is true. So if you have that exist x phi is in gamma, then there must be a k such that phi of k is in gamma. So why is that again? Because of the truth lemma. If an existential is in gamma, then we know that there is a witness for it in gamma. By induction hypothesis, we get that gamma forces this phi of k, which semantically implies that gamma forces the existential formula. And we do a similar trick for the universal, but this time not about membership, but about the negation of it. So if a universally quantified formula is not in gamma, then we want to have a witness k such that phi of k is not in gamma. The reason being that if we want a universally quantified formula to be false, we want to have a witness showing which witness this property does not hold. And so once again, this is just motivated by the truth lemma, by saying that if a universally quantified formula is not in gamma, then phi of k is not in gamma. By induction hypothesis, gamma does not force phi of k, and so gamma does not force the universally quantified formula. So that's all we need. Our canonical model, we need to have Henkin prime theories. And so note roughly that the disjunction case is already treated in the truth lemma, as well as the quantifiers, and the conjunction as well, because it's rather trivial. But yeah, so that's what we need. Now let's move on to the Lindenbaum lemma. To introduce the Lindenbaum lemma, and so this projection of a non-derivable consecution into the theories of a canonical model, I'll introduce a notation that introduces more symmetry in the notion of derivability or provability through these pairs gamma delta. So a pair gamma delta is provable if there exists a finite delta prime subset of delta such that gamma entails the disjunction of delta prime. So the idea is to provide the possibility to have gamma and delta infinite sets and not have a misbalanced, like an asymmetric take on what derivability means. So what we'll do is we'll start with an unprovable to expand what we'll expand is not a consecution anymore, but a pair that is not provable. And so we'll initiate with a pair that's gamma delta, which is not provable, with the restriction that gamma and delta must be closed, so they have no free variables. Why is that? When you think about it, we want to obtain at the end of the day Henkin properties. So the properties that Henkin theorists that do witness existentials in gamma and universals in delta. So we need to have fresh variables and enough of them to make sure that we can, along the way, make sure that our theory is indeed Henkin. And so that's why we require that gamma and delta are closed at the beginning. And so to extend them, we'll use an enumeration of the language of all the formulas with a specific property that at stage n, so when you go through the enumeration at the stage n, the variable n has not yet been used in the enumeration. So no formula up to now has been used the variable n. And so that will be very handy when we want to witness quantifiers. So when we say on our enumeration, when we encounter an existential formula, for example, we have this exist x phi. We ask the question, is it safe to add this formula to the left-hand side? What we really ask is this situation happening? So do we have still that by adding the existential formula on the left, we still haven't broken the non-provability of the pair? And if that's the case, then we need to find a witness for the existential formula, right? And so, well, quite luckily, we know that at this stage, we're at stage n, remember, the variable n hasn't been used yet, so we can rather safely add phi of n to the left-hand side as well. And so we do witness the existential. We do a similar trick for the universal quantifier, but this time on the right, we check whether it's fine to add the universal quantifier on the right. And if it is the case, then we need to witness it. And to witness it, we just use the variable n, which hasn't been used yet. And for all of the other formula, we check whether it's fine to add it on the left-hand side. And if so, do it, else you just add it to the right-hand side. So by looking at the structure of the formula, you know what to do in each case, and make sure that we obtain a Henkin property, a Henkin theory at the end of the day. And so we can prove actually that the resulting theory is Henkin and prime. So now, essentially, we've done the canonical model construction. We have our standard Lindenbaum lemma. So we call it standard because we have other non-conventional Lindenbaum lemmas that are following, but we have the Lindenbaum lemma. So now all we need to make sure of is that the truth lemma does go through. As I said, the truth lemma is done by induction on the structure of the formula, and we already know that the disjunction, conjunction, and quantifiers are dealt with. So all we need to be sure of is that the case of implication and the case of exclusion are okay in this context. And so let's start with the implication. So the tricky direction is the following one. You start with phi implies psi not being in gamma, and you want to show that gamma does not entail phi implies psi. So how do you do this? Well, the way that you do this is you can reason semantically. So let's see what we need to get to arrive on the right-hand side. We need to find a successor gamma prime of gamma, which forces phi, but not psi. This is just purely semantic. And so if we think again about the truth lemma situation where we have the induction hypothesis, we can know that it's sufficient to obtain a gamma prime, which is a superset of gamma, which contains phi, but not psi. Now, the question is, how on earth do you find this gamma prime? This is a bit puzzling because so far the Lindenbaum lemma that we had started from closed theories. So you had a rather strong restriction on what's a set of formulae you were starting with in order to expand it into a Hankin prime theory. But in this case, we have to start somehow from gamma and add phi to it, and then expand it into a Hankin prime theory, which does not contain psi. But clearly, gamma is not closed because it is a Hankin theory, and so it needs to witness a lot of existentially quantified formulae. And so this is a bit puzzling. And actually, we were a bit puzzled by this in our process of trying to find a completeness proof. But there is a trick that's given by Gabay, Shetman, and Skvortsov in their 2009 book called Quantification in Non-Classical Logics. And we're going to display it right now. So first of all, we do initiate our case of building up our new gamma prime with this situation with gamma and phi on the left, and we'll expand gamma and phi into a gamma prime by adding formulae on the right and left of the bar in the following way. So we have this gamma 0 and delta 0 that will build up through an enumeration once again by adding the formulae on the right or left of it. And so remember that given that we go through the enumeration, and so we only add formula through the enumeration, we know that gamma 0 and delta 0 at any time of our construction needs to be finite. So we can somehow think about it as having a big conjunction of gamma prime. This is a poor choice of prime because it could be called, like, say, gamma 0. That's not the gamma prime that we want to end up with. And on the right-hand side, we also have a big disjunction of delta. So once again, we have this enumeration, but how do we add stuff to our pair? Well, we need to make sure again that we have Hankin theories. So we need to make sure that if we add an extension on the left, we need to witness it. But then the problem of which variables do you pick, which variable do you pick to witness this existential formula comes up. So say that we can add safely the existential formula on the left-hand side. What do you do then? Then by having this scenario, you know through the deduction theorem that you can pull the formulae on the right-hand side. Then through intuitionistic logic laws, you can pull out the existential outside of the conjunction. And again, through an intuitionistic law, you know that this formula is entailed by the following one, where the for all x is quantifying over the entire implication. And so we know that this pair cannot be provable given the assumption that we had just before. And so in our scenario here, we have that gamma does not entail a universally quantified formula. But given that gamma is a Hankin prime theory, that means that this universally quantified formula is not in gamma. And so given that gamma is Hankin, it needs to provide a witness for it. And so we can find a witness that initially we're trying to find to witness our existential formula. So essentially, we will provide witnesses for our new construction gamma prime, for our new Hankin prime theory gamma prime, using the primeness, the Hankinness, sorry, of gamma itself. And we do a similar trick for the universal quantifier. So first, we ask whether it's fine to add it on the right. If that's the case, we're in this scenario. Then we do the deduction theorem. But now we can't play the same trick as before because we are in this situation where we have a universally quantified formula that's inside of a disjunction, but intuitionistically speaking, we're not allowed to pull it out. But that's a good time to remember to give you a reminder about the structure of the constant domain axiom that is effectively an axiom, a theorem of first order binds, which read from right to left allows you to pull out a universally quantified formula, a universally quantifier outside of a disjunction. And so that's effectively what we're using, and that's a crucial step of the proof, that you do pull out the universal quantifier by outside of the disjunction using the constant domain axiom. So that's what we can do. And then again, by intuitionistic reasoning, you can pull out the entire universal quantifier outside of the implication, and then you have again a weakness via Hankin-ness of gamma. And for all the other formulae, we just do as usual. So you can see that we did a bit of manipulation in trying to use the Hankin-ness of gamma to effectively provide witness in our construction of our gamma prime. So then we can build our gamma prime as described, and so we get that this case of the implication case for the truth lemma goes through. All we're left with is the exclusion case. The tricky part, and this is what is new. So the argument before was the one by Gabe, etc. But this time we provided a sort of dualized version of what they did, and that's for the exclusion case. So you start with phi excludes psi in gamma, and you want to show that gamma and forces phi excludes psi. Semantically, how do you do this? That means that you need to provide a predecessor of gamma prime of gamma, which forces phi but not psi. Once again, through the induction hypothesis, that means that we need to provide a sub-theory of gamma, which contains phi but not psi. Now, we need to provide this gamma prime. And how do we do this? Then it's even more puzzling, because while in the first case, we had this issue of how do we create witnesses, but still we were doing an expansion of the theory. So we're adding more stuff to it, which is the usual trick that you do in enumeration. While here, it seems that we need to take out from gamma in order to obtain this gamma prime. But how do we know what we can take out without breaking the properties of Hankin-ness or primeness? And so that's the puzzling bit, and we're not too sure how to do this. But this is where you need to flip your brain upside down, and where you need to realize that actually the restriction of a set is somehow an expansion of the complement of the set. So you can play this set theoretical game, and we will use, instead of having the gamma on the left, we'll use the complement of gamma on the right-hand side in our initial state. The idea being that all the formulae that we'll add on the left-hand side, all of them won't be in the complement of gamma. So that means that all of the formulas on the left that we'll add will have to be in gamma. And so the theory we'll end up with will be a subset of gamma. So we do a similar thing of considering conjunction and disjunction on the right. And now we need to give also witness for the existential and universal quantifiers when we encounter them in our enumeration. And so here we can't use the deduction theorem, which requires that we have the right-hand side, which is finite, but gamma complement is clearly not finite. But luckily, we're in bi-intuitionistic logic, and we can use the dual deduction theorem, which allows you to pull stuff from the right into the left-hand side. And in this case, we can then use the dual of the constant domain axiom, which is a formula of that shape, which is an anti-theorem. It's a contradiction. And by using this formula, it allows you, read from left to right, that to actually pull out an existential quantifier outside of a conjunction, which is exactly our case here. So that's what we do. And then we can pull out again through the laws of bi-intuitionistic logic. This is existential over the entire exclusion, which then gives you an existential quantifier, which is not in the complement of gamma, so which classically has to be in gamma. And because this is an existential quantifier, which is in gamma, and that gamma in Hankin, we need to have a witness. And I'm seeing that I'm short on time, and we can do something quite similar with the universal quantifier by doing the dual deduction theorem, then pulling out the universal quantifier outside of the disjunction, and then as an existential on the left, which gives us once more a witness. And any of other formulae, you just do the same. So what we've done essentially is we've completed all of the ingredients of canonical model construction, Lindenbaum lemma together with the truth lemma, that we make sure that all the cases went through. So we get strong completeness, showing that first order bind is indeed the conservative extension of first order constant domain int. And as you could see, it's a rather succinct proof because it's just a dualized tensor argument. And we also verified that proof to make sure that there was no mistake. So we formalized it in Coq. And as a follow-up to this work, we're considering diving into the algebraic notion of completeness. And because constructive for conservativity purposes, it's a bit better. And there are some interesting notions of completions. I want to have a look into this there. But anyway, that was it. That was it. Sorry for being a bit over time. And that was all from me.